What if you could move so fast that time itself bent around you? Picture this: you're hurtling through space at the speed of light, stars blurring into streaks, the universe stretching and warping in ways that defy logic. Now hold that thought, because out there in the cosmos, reality is even stranger. There are objects racing through the void at speeds so extreme, they make light seem sluggish. We're talking about cosmic bullets, hypervelocity stars ejected from galaxies like intercontinental missiles, black holes spinning so violently they fling matter across space at nearly light speed, and jets of plasma so powerful they could vaporize entire solar systems in a heartbeat. This isn't science fiction, it's the universe showing off. Across the unimaginable vastness of space, nature has crafted phenomena that push the limits of physics, rewriting the rules of speed itself. And today, we're diving headfirst into 30 of the most astonishing examples, each one a testament to the raw, untamed power of the cosmos. From stars torn free by supermassive black holes to particles accelerated to unfathomable energies, these are the universe's ultimate speed demons. But why does any of this matter? Because these cosmic speedsters aren't just thrilling curiosities, they're keys to unlocking some of the biggest mysteries in existence. They shape galaxies, trigger cataclysmic events, and even hint at the very fabric of space-time. So buckle up. We're about to take a ride through the fastest, most extreme corners of the universe, where the laws of physics are stretched to their breaking point, and where every discovery leaves us with more questions than answers. Ready to have your mind blown? Let's go. Imagine being flung out of your home galaxy so violently that you'd leave everything behind: planets, neighboring stars, even the pull of gravity itself. That's exactly what happens to hypervelocity stars, some of the fastest objects in the universe. These cosmic outlaws race through space at speeds exceeding 1 million miles per hour, so fast they could cross the entire United States in less than a second. And the force behind their incredible escape: a supermassive black hole lurking at the heart of their home galaxy. Here's how it works when a binary star system, two stars orbiting each other, wanders too close to a black hole. One star gets captured while the other is violently slingshotted away. The energy from this cosmic catapult launches the surviving star at speeds that defy the galaxy's gravity, sending it on a one-way trip into the void. One of the most famous examples is the so-called lone star, clocked at a staggering 1.6 million miles per hour. At that speed, it's not just leaving its galaxy behind, it's on track to escape the Milky Way entirely, becoming a true wanderer of intergalactic space. What's truly mind-blowing is that these stars aren't just rare oddities, they're cosmic messengers. By tracking their trajectories, astronomers can trace them back to the black holes that kicked them out, mapping the invisible forces shaping our universe. Each hypervelocity star is like a bullet fired from an unseen gun, telling a story of destruction, chaos, and the raw power lurking at the centers of galaxies. Now let's crank the speed dial up even further, to a place where entire stars spin faster than your blender on its highest setting. Meet pulsars, the universe's ultimate cosmic tops. These aren't just any stars, they're neutron stars, the collapsed cores of dead giants so dense a single sugar cube-sized chunk would weigh as much as Mount Everest. And when they spin, they don't mess around. Some rotate hundreds of times every second, their surfaces hurtling at nearly a quarter the speed of light. That means if you were standing on one, which you absolutely shouldn't try, you'd be flung into space before you could blink. The current gold medalist in this stellar speed contest is PSRJ 1748-2446 AD, spinning 716 times per second. At its equator, matter races at 24% light speed, so fast that if this pulsar were just a tad smaller, it would literally tear itself apart. But what makes these objects even more mesmerizing isn't just their dizzying rotations, it's the lighthouse effect they create. As they spin, their powerful magnetic fields beam radiation into space like a cosmic strobe light, sweeping across the universe with pinpoint precision. Some of these beams cross Earth's path, giving us regular pulses of radio waves so reliable they rival atomic clocks. Here's where it gets wild. That precision isn't just for show. Astronomers have used pulsars as interstellar GPS, even embedding their rhythms on the golden records sent with Voyager as a map for any potential extraterrestrial finders. But these spinning powerhouses aren't just celestial timekeepers, they're also laboratories for extreme physics. The forces at play here warp space-time itself, creating conditions so intense they challenge our understanding of matter and gravity. Every pulse we detect is a message from the edge of what's possible, a reminder that the universe has ways of breaking rules we didn't even know existed. But even pulsars can't hold a candle to the sheer violence of relativistic jets, cosmic fire hoses of plasma, blasting from black holes at 99% the speed of light. These aren't gentle streams, they're particle accelerators on a galactic scale, stretching tens of thousands of light years across space, dwarfing entire galaxies in their wake. Take the supermassive black hole at the heart of galaxy M87, for example. Its jet, captured in that iconic first-ever black hole image, is a searing beam of energy 5,000 light-years long, flinging matter so fast that time itself slows down for those particles in ways Einstein predicted over a century ago. How does something so extreme even exist? It starts with chaos. As matter spirals into a black hole's accretion disk, it doesn't just vanish quietly. Magnetic fields twist into colossal coils, turning the disk into a cosmic power plant. Some particles get caught in these magnetic tornadoes and are funneled toward the poles, where they're launched into space with unimaginable force. The energy behind this process is staggering, equivalent to converting the mass of entire stars into pure thrust. What's wild is that these jets aren't random. They're precision engines sculpted by physics into narrow beams that can pierce through interstellar gas without dispersing. That's why we can see them across cosmic distances, like a lighthouse cutting through fog. And their impact, these jets are cosmic landscapers, carving out bubbles in galaxy clusters and even shutting down star formation by overheating surrounding gas. They're proof that black holes aren't just destroyers, they're architects, shaping the universe on scales we're only beginning to understand. Now, let's zoom in from the colossal to the incomprehensibly tiny. Particles so small they're invisible, yet pack punches that would make a supernova flinch. Meet cosmic rays, the universe's ultimate microscopic speedsters. These aren't your average subatomic particles, they're bullets of pure energy, screaming through space at velocities so close to light speed that the difference is almost immeasurable. At the top of this cosmic leaderboard sits the legendary, oh my god, proton, detected in 1991, hurtling toward Earth at 99.999999% the speed of light. To put that into perspective, if this particle were a baseball, its energy would rival a fastball pitched by a major leaguer, except it's a single proton, a speck billions of times smaller than a grain of sand. So where does something this ferocious come from? That's the million-dollar question. The sheer energy of these particles suggests they're born from the most violent events in the universe: supernova explosions, colliding neutron stars, or the jets of supermassive black holes. Yet, even these extreme scenarios struggle to explain the upper limits of cosmic ray energy. Some theories point to active galactic nuclei, where magnetic fields act like cosmic railguns, or to mysterious, dark matter annihilations phenomena we're still struggling to decode. What's certain is that these particles have traveled millions, possibly billions of light years, threading through galaxies and magnetic fields without slowing down, only to collide with Earth's atmosphere in a spectacular burst of secondary particles. The real kicker: we're being bombarded by these things all the time. Most cosmic rays are lower energy, but even the average ones are moving at significant fractions of light speed. When they strike our atmosphere, they trigger cascades of particles detectable by ground-based observatories. Scientists use these air showers like cosmic fingerprints, tracing the particles back to their origins. But the highest energy ones, like the oh my god particle, they're so rare that detecting even a handful over decades feels like winning the lottery. Each one is a messenger from the most extreme corners of the cosmos, carrying secrets about how the universe accelerates matter to such insane velocities. Think about this the next time you feel a raindrop somewhere above you. A proton that's been racing through the void since before Earth existed just slammed into the air, unleashing energy that defies comprehension. And we're only beginning to unravel what it's trying to tell us. Black holes aren't just cosmic vacuum cleaners, they're celestial cannonballs, capable of being launched across the universe at unimaginable speeds. Take the case of 3C186, a supermassive black hole caught in the act of fleeing its home galaxy at 4.7 million miles per hour. That's fast enough to travel from Earth to the Moon in under 3 minutes. What kind of force could possibly eject something with the mass of a billion suns? The answer lies in one of the most violent events in existence, a cosmic collision between galaxies. When two galaxies merge, their central black holes eventually spiral toward each other, locked in a gravitational dance. As they orbit closer, they emit ripples in space-time called gravitational waves. In rare cases, if these waves aren't perfectly symmetrical, the final merger can kick the newborn black hole in the opposite direction like a rocket recoiling after firing. The numbers are staggering. The energy released in this recoil can rival the combined light of every star in the Milky Way for an entire minute. That's enough thrust to send a black hole screaming into the void, dragging its surrounding gas and stars along like a cosmic comet tail. What's eerie is the aftermath. The ejected black hole leaves behind a galaxy suddenly missing its gravitational anchor. Stars that once orbited neatly around the center now drift in confused, elongated paths. Meanwhile, the runaway black hole becomes a nomad, blazing through intergalactic space and potentially seeding new galaxies with its entourage of trapped stars. Some theories even suggest these roving behemoths could explain mysterious, orphaned quasars, bright, active nuclei with no visible host galaxy. The discovery of 3C186 wasn't just luck. Astronomers spotted its telltale signature, a quasar glowing 25,000 light-years away from its galaxy's center, trailing a bridge of young, violently heated stars. Follow-up observations revealed the staggering truth. This black hole wasn't just displaced, it was escaping for good, with enough speed to leave its galaxy forever in roughly 20 million years. And it's likely not alone. Simulations suggest thousands of these rogue black holes could be wandering the cosmic dark, invisible except for the faint glow of any gas they've dragged along. Imagine the scene: a titan of destruction, born from a cataclysmic merger, now racing through emptiness at speeds that defy comprehension. It's a reminder that even the mightiest objects in the universe aren't anchored in place. Gravity can build empires and then, with a flick of spacetime itself, tear them apart. Gamma-ray bursts are the universe's ultimate power plays, brief, blinding flashes that outshine entire galaxies for a few fleeting seconds, then vanish without a trace. But hidden within these cosmic fireworks lies something even more extraordinary: ultra-relativistic jets screaming through space at 99.99% the speed of light. These aren't just beams of energy, they're particle accelerators on a scale that makes the Large Hadron Collider look like a toy, twisting the laws of physics into knots. The numbers alone defy comprehension. In just 1 second, a single gamma-ray burst can release more energy than our Sun will emit in its entire 10 billion-year lifetime. And the jets responsible, they're so tightly focused that if you aimed one at Earth from across the universe, its beam would be narrower than a pencil's width by the time it reached us. One of the most intense bursts ever recorded, GRB 080319b, hurled matter so fast that time dilation would mean a minute in the jet would stretch to nearly 3 hours for an outside observer. What fuels such apocalyptic speed? The leading theory points to the birth of a black hole, either from the collapse of a hypermassive star or the cataclysmic merger of two neutron stars. As the newborn black hole devours its surroundings, intense magnetic fields channel infalling material into twin jets erupting from its poles. But here's where it gets weird. These jets don't just coast. They're rammed through layers of collapsing star matter like a bullet through tissue paper, gaining speed until they're moving at a hair's breadth below light speed. The friction within these jets is so extreme that particles slam together with enough force to forge gold, platinum, and other heavy elements in seconds, scattering precious metals across the cosmos like interstellar confetti. The real magic happens when these jets plow into surrounding gas. That collision creates an afterglow, a fading fingerprint of lower energy radiation that can linger for weeks. It's this afterglow that gives astronomers their best clues. By analyzing its light curve, they've discovered these jets aren't smooth streams but lumpy, with internal shock waves acting like cosmic speed bumps. Some particles get extra kicks from these shocks, reaching energies so high they shouldn't exist under known physics. Perhaps the most haunting discovery is the link between gamma-ray bursts and supernova. In several cases, telescopes caught the telltale signs of a star's explosive death lurking beneath the burst's afterglow. This suggests some bursts are the death cries of stars 30 to 40 times more massive than our Sun, stars so unstable they don't just die, they detonate with enough force to hurl their guts across galaxies. Yet, even among these stellar catastrophes, gamma-ray bursts are the rare elite. Only 1 in every 100 supernova produces one, making them the universe's most exclusive and destructive members-only club. Every burst we detect is like finding a message in a bottle from the edge of reality. Written in X-rays and gamma rays, these messages tell of gravitational maelstroms, matter pushed beyond its limits, and energies that rewrite the rules. And somewhere out there, right now, another jet could be forming. A spear of pure velocity aimed at the darkness, ready to pierce the cosmos and remind us how small our corner of existence truly is. Some cosmic dances defy all expectations, none more breathtaking than the death spiral of Cancri, a pair of white dwarfs locked in the fastest orbital waltz ever witnessed. These two stellar corpses, each packing a sun's worth of mass into an Earth-sized sphere, whip around each other at a mind-numbing 1.8 million miles per hour, completing a full orbit every 5 minutes. That's faster than a fighter jet crossing the continental United States in the time it takes to microwave popcorn. And this isn't just a cosmic oddity. It's a precision laboratory for testing the very fabric of reality under conditions Einstein himself could only dream of. The mechanics of this system are dizzying. The stars orbit so close that their surfaces would fit inside the Sun with room to spare, separated by just a few 100,000 miles, less than the distance from Earth to the Moon. At this proximity, their gravitational tug is so intense that spacetime around them warps like a trampoline stretched to its limit. Every rotation sends ripples through the cosmic fabric, energy bleeding away as gravitational waves. The same phenomena detected by LIGO from colliding black holes, but here playing out in a continuous, measurable hum. What makes Cancri extraordinary isn't just its speed, but its clockwork predictability. Einstein's theory predicted that such tight orbits would decay over time as energy is lost to gravitational radiation. Sure enough, observations reveal the stars spiraling inward by about 2 inches per orbit, their dance gradually tightening. This minuscule drift might sound insignificant, but over decades it adds up to a perfect test of relativity. The match between prediction and observation is so precise that it leaves less than 1% room for error, a resounding confirmation of equations scribbled on paper a century ago. Yet the surprises don't stop there. The system's breakneck motion creates wild tidal forces, stretching the white dwarfs into egg-shaped ovals as they whirl. This distortion affects how light escapes their surfaces, causing the system's brightness to pulse like a strobe light with each orbit. Astronomers have turned these flickers into a cosmic stopwatch, tracking orbital changes down to millisecond accuracy. It's like using the heartbeat of a star to measure the curvature of the universe. But perhaps the most haunting detail is Cancri's fate. In about 300,000 years, a blink in cosmic time, these stars will collide, triggering a titanic explosion known as a Type Ia supernova. For a brief moment, they'll outshine entire galaxies, scattering heavy elements forged in their final embrace across the cosmos. Until then, they'll keep spinning faster and closer, a relentless countdown to apocalypse written in the language of gravity and light. Every second of their dance is a masterpiece of physics, a reminder that even in death, stars can teach us the universe's deepest secrets. Quasars aren't just the universe's brightest beacons, they're cosmic pressure washers, blasting galaxies with winds so fierce they reshape entire neighborhoods of space. At the heart of these phenomena lie quasar outflows, hurricanes of superheated gas screaming outward at 20% light speed over 130 million miles per hour. That's fast enough to cross Earth's orbit in under 40 minutes. These aren't gentle breezes, they're tsunamis of energy, capable of sweeping away entire reservoirs of star-forming gas like a leaf blower clearing a sidewalk. Picture the forces at work here. A supermassive black hole gorges on surrounding matter, its accretion disk glowing white-hot with friction, but not all that material falls inward. Magnetic fields and radiation pressure funnel some gas into bipolar jets, launching it into the void with enough force to counteract the black hole's crushing gravity. The result, a feedback loop of staggering violence. For every sun's worth of material the black hole devours, it spits back out a fraction with enough energy to clear cubic light-years of space. The impact is cosmic gardening on a grand scale. In younger galaxies, these outflows act like a thermostat, preventing runaway star formation by ejecting the cold gas needed to birth new stars. Observations of quasar SDSS J1106+1938 reveal outflow winds so powerful they'd empty our Milky Way of star-forming fuel in just 10 million years, a geological eye blink. Yet paradoxically, these same winds can compress remaining gas in their wake, triggering secondary bursts of star formation in their outer edges. It's a delicate balance, too little outflow and galaxies overheat with frenzied starbirth, too much and they're left barren and aging prematurely. What's truly mind-bending is the scale of energy transport. A single quasar outflow can carry kinetic energy equivalent to 10,000 supernova per year energy that eventually dissipates into intergalactic space, heating the cosmic web itself. The Atacama Large Millimeter Array has spotted these winds depositing heavy elements billions of light-years from their origin, chemically enriching voids that might otherwise remain pristine. Recent simulations show these outflows may solve a long-standing mystery: why the universe's star formation rate peaked billions of years ago and has been declining since. The answer might lie in quasars' golden age, when their winds systematically starved galaxies of raw materials. Every jet of ultrafast gas was a vote against unchecked cosmic growth, a reminder that even in the universe, sometimes you need to clear the table before new things can begin. Kepler 70b isn't just a planet. It's a cosmic drag racer hurtling around its star at 1.5 million miles per hour, turning an entire year into less than 6 Earth hours. Imagine a world where New Year's Eve fireworks would go off 4 times a day. This exoplanet exists in a realm of extremes, so close to its host star that it defies everything we know about planetary survival. The star, Kepler 70, is a burnt-out stellar corpse, a subdwarf that shed its outer layers, leaving behind a searing hot core 5 times hotter than our Sun. And orbiting just 850,000 miles away, closer than Mercury gets to our Sun, this planet is essentially skimming the surface of a nuclear furnace. The physics at play here are brutal. Kepler 70b isn't just tidally locked, it's being actively vaporized. One hemisphere permanently faces the star, baked to temperatures exceeding 6,800 degrees Fahrenheit hotter than some stars. The day side is an ocean of molten rock and metallic vapor, where elements like iron don't just melt but become gaseous, creating a shimmering, hellish atmosphere. Meanwhile, the night side, if you can call it that, is a mere 3,600 degrees cooler, still hot enough to melt lead. The temperature difference between both sides generates supersonic winds, howling at thousands of miles per hour as they try and fail to redistribute the insane heat. What's truly staggering is how this planet even exists. Most worlds this close to their stars would have been torn apart by gravitational forces or evaporated entirely. Yet Kepler 70b clings on, its dense, possibly iron-rich core resisting annihilation. Some astronomers speculate it might be the stripped-down remnant of a gas giant, its atmosphere boiled away over eons, leaving behind a charred, metallic skeleton. Others suggest it could be the product of a cataclysmic collision, a survivor of some ancient planetary demolition derby. The star itself adds another layer of madness. Kepler 70 isn't just any star, it's a pulsating variable, rhythmically expanding and contracting like a cosmic heartbeat. These oscillations create bursts of intense radiation that hammer the planet's already blistering surface, turning its orbit into a deadly obstacle course. Yet despite the violence, the planet's breakneck speed keeps it stable, a testament to the delicate balance between gravity and motion. Kepler 70b is more than a curiosity, it's a preview of our solar system's fate. In 5 billion years, when our Sun swells into a red giant before collapsing into a white dwarf, inner planets like Mercury and Venus may share this world's fiery destiny. For now, though, it stands alone as the fastest known exoplanet, a scorched sentinel racing through the ashes of its star's former glory. Every orbit is a reminder, the universe doesn't just create worlds, it forges them in fire. Messier 82 isn't just a galaxy, it's a cosmic pressure cooker, blasting out hurricanes of superheated gas at 2 million miles per hour. Known as the cigar galaxy for its elongated shape, this starburst powerhouse is birthing stars at a rate 10 times faster than our Milky Way, and the fallout is spectacular. Every year, the equivalent of 10 suns worth of gas gets ejected into intergalactic space, not as a gentle breeze but as a supersonic shockwave capable of reshaping its cosmic neighborhood. At the heart of this chaos lies a simple but violent equation: too many stars, too close together. In Messier 82's crowded core, supernovae explode like fireworks in quick succession, their combined force punching holes in the galaxy's gas reservoirs. These explosions create a feedback loop. Each detonation heats surrounding gas, which then expands and triggers more star formation, leading to more supernova. The result, a self-sustaining tempest that astronomers call a galactic superwind. Picture the entire galaxy coughing up its guts, spewing oxygen, carbon, and heavier elements like iron into the void at speeds that defy gravity's pull. What's truly groundbreaking is where this material ends up. The Hubble Space Telescope has traced filaments of metal-rich gas stretching tens of thousands of light-years beyond Messier 82's disk, far enough to reach neighboring galaxies. These aren't just random streaks, they're cosmic supply chains delivering the raw ingredients for future stars and planets to regions that would otherwise lack them. In a way, starburst galaxies like this are the universe's recyclers, taking heavy elements forged in stellar furnaces and scattering them across intergalactic space like seeds in the wind. But here's the twist: these superwinds don't just spread creation, they also bring destruction. The same forces that eject gas can strip smaller satellite galaxies of their star-forming material, leaving them barren and aging prematurely. It's a cosmic balancing act where one galaxy's frenzied starbirth comes at the expense of others' futures. Observations show that without these winds, galaxies like Messier 82 would exhaust their gas reserves in just a few 100 million years, burning out in a flash rather than sustaining star formation over billions of years. The legacy of these superwinds is written across the universe. When astronomers analyze distant intergalactic gas clouds, they find the same elemental fingerprints as those in Messier 82's outflows. These metals, forged in supernova and carried by galactic winds, now float in the spaces between galaxies, invisible except for the faint absorption lines they create in quasar light. They're ghosts of ancient starbursts, remind us that even the emptiest voids were once touched by fire. So next time you gaze at the Cigar Galaxy through a telescope, remember, you're not just seeing a collection of stars. You're witnessing a galactic engine, one that's been churning out stars and spewing their remains across the cosmos for millions of years. It's messy, violent, and utterly essential to the story of how our universe built the ingredients for everything, including us. Tucked away beneath the Antarctic ice, a telescope unlike any other hunts for cosmic ghosts, neutrinos, the universe's stealth speedsters. These nearly massless particles are the ultimate minimalist travelers, zipping through space at 99.9999% the speed of light, so close to the universal speed limit that if light were a sports car, neutrinos would be tailgating it with their high beams on. What's staggering isn't just their velocity, it's how effortlessly they slice through the cosmos, passing through planets, stars, and even you right now without a trace. Yet when these phantoms collide with something unwilling to let them pass, like the ultra-pure ice of the Ice Cube Neutrino Observatory, they reveal secrets about the most violent events in existence. Take the case of one neutrino dubbed Big Bird, detected in 2013 with energy so colossal it made physicists double-check their instruments. Tracing its path backward led astronomers to a blazar 4 billion light-years away, a supermassive black hole firing jets directly at Earth. This single particle had raced across the universe, untouched by magnetic fields or interstellar gas, carrying a fingerprint of its origin like a cosmic bullet with a return address. But why do neutrinos move so fast? The answer lies in their bizarre physics. Unlike light, which slows down when passing through matter, neutrinos barely interact with anything. They're born in extreme environments, supernova explosions, colliding neutron stars, or the accretion disks of black holes, where particles are accelerated to insane energies. Yet because they carry no charge and almost no mass, nothing slows them down. A neutrino produced in the sun's core reaches Earth just 8 minutes after light does, despite plowing through 400,000 miles of dense stellar material that would stop photons in their tracks. Detecting these particles requires ingenuity. Ice Cube sensors are buried over a mile deep in Antarctic ice, waiting for the rare moment a neutrino smashes into an atomic nucleus. The collision creates a secondary particle called a muon, which streaks through the ice faster than light can travel in that medium. Yes, faster than light in ice, producing an eerie blue glow called Cherenkov radiation. It's this flash that Ice Cube's photomultipliers capture, transforming an invisible particle's passage into data. The real magic comes when multiple detectors worldwide collaborate. In 2018, Ice Cube spotted a neutrino and alerted telescopes within seconds. Within hours, observatories from gamma-ray to radio swung toward its origin, catching a blazar in the act of shredding matter. This multi-messenger astronomy, combining light, neutrinos, and even gravitational waves, is rewriting how we study the cosmos. Neutrinos aren't just cosmic speed records. They're messengers from places light can't escape, carrying news from the universe's darkest corners. Think about that next time you stand in sunlight. Trillions of neutrinos from our sun's core are passing through your body every second, remnants of nuclear reactions that started their journey 8 minutes ago. They've traveled unimpeded through the sun's bulk, across the vacuum of space, and now through you silent witnesses to how the universe moves at the edge of possibility. And somewhere out there, another neutrino is racing toward Earth right now, carrying a story we've only begun to decode. At the heart of the Virgo cluster, a galactic heavyweight spins with such ferocity that its outer stars should be flung into the void, yet they cling on, defying every expectation. Messier 87, the supermassive elliptical galaxy famous for hosting the first photographed black hole, harbors another astonishing secret: stars racing around its outskirts at 1.2 million miles per hour, dizzying speeds that shouldn't be possible based on visible matter alone. This cosmic conundrum begins with simple physics. Just as a merry-go-round spins faster when weighted toward the center, galaxies typically rotate slower at their edges unless something invisible is anchoring them. In Messier 87's case, the outer star's velocity suggests the galaxy contains up to 100 times more mass than what telescopes can see. The culprit, a sprawling halo of dark matter, its gravitational tendrils weaving an unseen scaffold that keeps these stellar speedsters from escaping. But how do we measure something invisible? Astronomers track the Doppler shifts of stars orbiting the galaxy's fringe. Those moving toward us glow slightly bluer, while those receding appear redder. The staggering velocity revealed by these color changes paints a startling picture. Without dark matter's grip, Messier 87 would unravel like a spinning pizza dough flung too fast. What's truly fascinating is how this galaxy compares to our own. While the Milky Way's rotation curve flattens at its edges, a classic dark matter signature, Messier 87's speed surge, thanks to its monstrous central black hole and the dense cluster environment. This black hole, weighing 6.5 billion suns, warps spacetime so intensely that even distant stars feel its pull. Combine that with the galaxy's collision-rich histories, wallowing smaller galaxies like cosmic snacks, and you've got a gravitational maelstrom where dark matter and visible matter dance in ways we're still deciphering. Recent simulations suggest Messier 87's dark matter halo might resemble a flattened sphere stretched by eons of galactic interactions. Its sheer scale boggles the mind. Trillions of unseen particles stretch nearly 2 million light-years from the core, far beyond the galaxy's visible edge. Some theories propose these particles could be weakly interacting massive particles, while others speculate about primordial black holes sprinkled through the halo. Every star whipping around Messier 87's outskirts is a testament to the universe's hidden architecture. They're not just breaking speed records, they're mapping the invisible scaffolding that holds galaxies together, one dizzying orbit at a time. When our sun gets angry, it doesn't just sulk. It hurls entire chunks of itself into space at speeds that would put any human-made rocket to shame. Coronal mass ejections are the solar system's most violent tantrums, blasting up to 1 billion tons of superheated plasma outward at 6 million miles per hour. That's fast enough to cross the distance from New York to Tokyo in less than a second. These aren't gentle waves of particles, they're tsunamis of magnetized gas, carrying enough energy to power global civilization for 20,000 years if we could somehow harness it. The physics behind these eruptions is like a pressure cooker with no release valve. Tangled magnetic fields on the sun's surface snap like overloaded rubber bands, suddenly releasing pent-up energy. The resulting explosion lifts part of the sun's corona, its outer atmosphere clean off the surface, accelerating it to insane velocities. Imagine stretching a slingshot across the entire length of Earth's orbit, now let go. That's the scale of acceleration we're talking about. When one of these solar storms hits Earth, the results are both beautiful and terrifying. The collision with our magnetic field creates auroras so intense they've been mistaken for daylight, like the famous 1859 Carrington event when northern lights were seen as far south as Cuba. But the same electromagnetic forces that paint the sky can also fry satellites, knock out power grids, and scramble radio communications. In 1989, a geomagnetic storm triggered by a coronal mass ejection left 6 million people in Quebec without electricity for 9 hours. Modern technology makes us even more vulnerable. A Carrington-level event today could disable GPS systems for days, disrupt air travel, and potentially damage undersea internet cables. NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter now provide early warnings, tracking these plasma storms as they race toward us. Their footage reveals coronal mass ejections as twisting helices of charged particles, sculpted by interplanetary magnetic fields into shapes resembling celestial DNA. Yet there's an irony to these destructive powerhouses. Without them, life might not exist. Over billions of years, solar storms helped distribute elements crucial for life across the solar system, and some theories suggest they may have even delivered the energetic spark needed for Earth's first organic molecules. Today, astronauts on the International Space Station occasionally see flashes in their eyes when particularly energetic particles zip through their retinas, a personal light show courtesy of our tempestuous star. The next time you see an aurora's shimmering curtain, remember, you're witnessing the aftermath of a cosmic particle cannon, firing magnetized plasma across 93 million miles of space with pinpoint accuracy. It's a reminder that even our seemingly steady sun is a seething ball of plasma with the power to reach out and touch us, sometimes gently, sometimes with the force of a celestial wrecking ball. While cosmic objects routinely shatter speed records set by nature, humanity's fastest spacecraft seems downright sluggish in comparison. NASA's Parker Solar Probe currently holds our species' speed championship, screaming through the inner solar system at 430,000 miles per hour, fast enough to circle Earth's equator in under 4 minutes. Yet when placed against the cosmic leaderboard, that impressive velocity barely registers at 0.06% of light speed. The physics behind this disparity reveals why interstellar travel remains so daunting. The Parker probe achieves its blistering pace through gravity-assist slingshot maneuvers around Venus that trade planetary momentum for speed. Each close pass adds another push, like a cosmic skateboarder kicking off successive ramps. During its closest solar approach, the probe endures temperatures exceeding 2,500 degrees Fahrenheit behind its revolutionary heat shield, all to study the Sun's mysterious corona at closer range than any object in history. What's humbling is how this engineering marvel compares to natural particle accelerators. While the Parker probe's speed would get you from New York to Los Angeles in about 20 seconds, cosmic rays routinely whip past at 99.999999% light speed. The energy difference is staggering. Our fastest spacecraft carries the kinetic energy of about 1 gram of TNT, while the "oh my god" particle mentioned earlier packed the punch of a major league fastball in a single proton. Even spacecraft speed records have an expiration date. The Parker probe will eventually lose momentum to solar gravity, while hypervelocity stars and relativistic jets maintain their cosmic sprints indefinitely. This stark contrast highlights the fundamental challenge of space travel. Without harnessing the extreme physics of black holes or pulsars, we're limited to crawling through our local stellar neighborhood at a snail's pace compared to the universe's natural speed demons. Yet the Parker probe represents a crucial step toward understanding these cosmic accelerators. By studying how the sun's corona heats to millions of degrees while the surface stays relatively cool, scientists gain insights into the same plasma physics that power quasar jets and supernova remnants. Every data point radioed back from this scorching mission helps decode the universal mechanisms that accelerate particles to velocities we can only dream of achieving. Perhaps most poetically, the probe's instruments have detected the faint trails of hypervelocity dust particles, microscopic projectiles, accelerated by solar radiation to speeds even faster than the spacecraft itself. These motes, smaller than a red blood cell but moving at over 1 million miles per hour, offer a tantalizing glimpse of how nature effortlessly outperforms our most ambitious engineering. They serve as quiet reminders that while we've conquered solar system speeds, the universe still holds the ultimate racing trophies. When two neutron stars spiraled into each other in a galaxy 130 million light-years away, they didn't just collide, they detonated a cosmic forge that showered the universe with gold at nearly a third the speed of light. The event, catalogued as GW170817, wasn't just the first neutron-star merger detected via gravitational waves. It was humanity's front-row seat to witnessing the birth of precious metals on an unimaginable scale. The numbers alone boggle the mind, as the stars, each more massive than our Sun, yet only 12 miles across, finally merged. Their collision unleashed jets of neutron-rich material at 30% light speed. That's over 200 million miles per hour, fast enough to cross Earth's orbit in under 20 minutes. But what makes this debris truly extraordinary isn't just its velocity, it's what it carried. Simulations suggest the explosion created a swirling maelstrom of extreme conditions, where atomic nuclei were bombarded with neutrons so rapidly they ballooned into heavy elements like gold, platinum, and uranium. The estimated yield, at least 10 Earth masses of pure gold alone, along with other rare metals worth, well, more than every economy on Earth combined. What's wild is how we caught this event in action. The gravitational wave signal tipped off astronomers first, a faint chirp lasting barely 100 seconds as the stars completed their death spiral. Just 1.7 seconds later, NASA Fermi satellite detected a gamma-ray burst from the same patch of sky. Within hours, telescopes around the world swiveled toward the source, capturing something never seen before, a kilonova, its glow shifting from blue to red as heavy elements formed in real time. Spectroscopy revealed telltale absorption lines of strontium and other neutron capture elements, confirming theorists' predictions about where the universe's heavy elements originate. The aftermath played out like a cosmic fireworks finale. For days, the expanding debris cloud radiated with the heat of nuclear reactions, glowing brighter than a million suns. Matter ejected sideways, slower but richer in heavy elements, formed a lopsided halo, while the faster polar jets punched through interstellar gas like searchlights. Hubble Space Telescope observations later found that this single event likely seeded its host galaxy with enough gold to gild every planet in its solar system 20 times over. But here's the real kicker. GW170817 wasn't a freak accident. Estimates suggest these mergers happen roughly once every 100,000 years per galaxy, meaning the cosmos has been conducting this alchemy since the first stars died. That gold ring on your finger, it probably began its existence in a similar cataclysm billions of years ago, hurled across space at relativistic speeds before eventually finding its way into a molecular cloud, then a protoplanetary disk, and finally Earth's crust. Every precious metal we cherish is stardust, yes, but more specifically, it's the fallout from the universe's most extreme smash-ups. The legacy of this one cosmic collision ripples far beyond jewelry boxes. By studying kilonova ejecta, scientists are decoding how elements essential for life, like iodine and uranium, spread through galaxies. Some theories even suggest these events could explain mysterious, heavy element pockets in ancient stars. What seemed like an esoteric gravitational wave detection has become a Rosetta Stone for understanding our chemical origins, proving that sometimes the universe's fastest phenomena leave the most enduring marks. Deep in the heart of our galaxy, a star defies all expectations not just by surviving the gravitational maw of a supermassive black hole, but by whipping around it faster than any known object in the Milky Way. S4714, a seemingly ordinary blue star, races through space at 15 million miles per hour, tracing an orbit so tight it loops Sagittarius, a star, in just 7.6 years. To put that velocity into perspective, this stellar speedster could lap Earth's equator in less than 2 seconds, leaving supersonic jets in the dust. What makes S4714 extraordinary isn't just its breakneck pace, it's the cosmic obstacle course it navigates. Orbiting just 9 billion miles from the black hole's event horizon, closer than Pluto is to our Sun, the star endures space-time so warped that general relativity shifts from theory to visceral reality. Imagine trying to sprint full tilt on a trampoline while someone hurls bowling balls onto the fabric beneath you. That's the chaotic gravitational landscape this star contends with. Einstein's equations predict that at such proximity, the black hole's spin drags space-time around it like a whirlpool, twisting S4714's orbit into a rosette pattern rather than a simple ellipse. The discovery shattered assumptions about stellar survival. Conventional wisdom held that black holes this close would shred stars apart through tidal forces. Yet S4714's compact size, likely no larger than our Sun, allows it to withstand gravitational extremes that would stretch larger stars into spaghetti-like streams. Infrared observations from the Keck and Very Large telescopes revealed its telltale blue glow amid the galactic center's dust clouds, its Doppler-shifted light confirming velocities that demand a black hole 4 million times the Sun's mass to keep it bound. But here's the real puzzle. How did it get there? One theory suggests the star was part of a binary system that wandered too close. As the black hole captured its companion, S4714 received a gravitational slingshot kick, settling into this improbable orbit. Alternatively, it might be a refugee from a dense star cluster, its path sculpted by countless close encounters before the black hole claimed it. Whatever its origin, each close pass steals a bit of the star's orbital energy, meaning in a few thousand years, it will spiral ever closer toward oblivion, offering astronomers a front-row seat to stellar demise in extreme gravity. For scientists, S4714 is more than a record holder. It's a precision tool. By tracking its movement, they've refined estimates of Sagittarius, a star's mass and spin with unprecedented accuracy. The star's path also serves as a real-time test of relativity. Subtle deviations from predicted orbits could hint at new physics lurking near black holes. Future telescopes like the 30-meter telescope aim to monitor its dance in even greater detail, potentially revealing if dark matter or other unseen forces tweak its trajectory. This stellar daredevil reminds us that the universe's fastest objects aren't always the most obvious. Sometimes they're quiet survivors, threading the needle between destruction and discovery, rewriting textbooks one breakneck orbit at a time. Dark matter doesn't just lurk in halos around galaxies, it rivers through the cosmos in high-speed torrents, weaving an invisible web that shapes everything we see. These so-called dark matter streams are the universe's hidden highways, funneling unseen particles at millions of miles per hour, their presence betrayed only by the way they warp the fabric of spacetime itself. Picture a mountain stream, but instead of water, it's an undetectable fluid of exotic particles, carving channels through galaxies so smoothly that stars drift through them without a bump. The first clues to these streams came from gravitational lensing, nature's version of a funhouse mirror. When light from distant galaxies passes through massive objects, their gravity bends the light's path like a prism. But sometimes the distortion reveals something odd, thin, elongated streaks where no visible matter exists. These are the fingerprints of dark matter streams, their gravity tugging on light despite being utterly transparent. In 2016, Hubble spotted a lensed galaxy stretched into a hair-thin arc, a cosmic mirage pointing to a dark matter filament as massive as a galaxy cluster yet completely invisible. What's staggering is the scale. Simulations suggest our own Milky Way swims in a network of these streams, some as wide as the solar system, others spanning thousands of light years. The fastest flow identified to date, dubbed the Virgo overdensity stream, barrels through our galactic neighborhood at 2 million miles per hour. Particles so ethereal they pass through your body like moonlight through glass, yet collectively holding enough mass to steer entire galaxies. The origins of these rivers trace back to the universe's infancy. In the early cosmos, dark matter clumped into a vast cosmic web under gravity's pull, while ordinary matter pooled in its densest intersections to form galaxies. The lesser tributaries, they remained as streams, pristine relics of the universe's structure before stars even lit up. Some may be the shredded remains of dwarf galaxies torn apart by tidal forces, their dark matter unraveling into ribbons that still orbit their conquerors. But here's the twist: these streams aren't just fossils, they're actively sculpting galaxies today. As the Sagittarius dwarf galaxy disintegrates around the Milky Way, its dark matter forms a spiraling current that might be warping our galaxy's disk. Other streams could explain why some galaxies rotate faster at their edges than visible matter allows their hidden momentum supplied by these rushing, unseen rivers. Even our solar system might be crossing a local dark matter trickle, a possibility that fuels experiments hoping to catch these elusive particles as they whistle past Earth. The hunt for streams is rewriting cosmology. By mapping their distribution through lensing surveys, astronomers are piecing together how dark matter behaves, whether it's cold and sluggish or warm and fast-moving. Each new filament discovered is a thread in the grand tapestry of cosmic structure, revealing how the universe's hidden architecture guides the dance of galaxies. And somewhere out there, a stream we've yet to detect could be flowing right through us, carrying secrets about the 85% of matter that makes up the universe but refuses to shine. GRS 1915+105 isn't just a black hole. It's a cosmic tornado, spinning so violently it twists the fabric of reality around itself at 1,150 rotations every second. That's not a typo. At this speed, its event horizon isn't just a boundary, it's a blur dragging space-time along like molasses caught in a whirlpool. The sheer force of its rotation creates conditions so extreme that Einstein's equations start bending over backward trying to describe them. Let's break down what this means. Most black holes rotate, but GRS 1915+105 is in a league of its own, spinning at over 90% of the theoretical maximum speed allowed by physics. At this rate, the centrifugal forces are so intense that the singularity inside isn't a point, it's stretched into a ring, a phenomenon predicted by mathematician Roy Kerr back in 1963. Surrounding this ring is the ergosphere, a region where spacetime itself gets caught in the black hole's rotation, forcing everything, even light, to move in the same direction. Think of it like standing on a merry-go-round spinning so fast you'd be flung off, except here, the merry-go-round is made of warped spacetime and there's no getting off. What's wild is how we even measure this spin. Unlike stars or planets, black holes don't have surfaces to track. Instead, astronomers study the behavior of their accretion disk, superheated gas spiraling inward. For GRS 1915+105, X-ray observations revealed telltale flickers caused by material being stretched and squeezed as it orbits just outside the event horizon. The frequency of these flickers acts like a cosmic tachometer, letting scientists calculate the spin with surprising precision. But here's where it gets stranger. This black hole isn't just spinning fast, it's firing off relativistic jets at 90% light speed, twisting magnetic fields into cosmic particle accelerators. These jets aren't steady, they pulse in rhythmic bursts like a celestial strobe light, as infalling matter gets whipped around the black hole's equator before being launched poleward. Some theories suggest the jets might even be tapping into the black hole's rotational energy directly, like a thief stealing momentum from a spinning top. The implications ripple far beyond this one black hole. GRS 1915+105 challenges our understanding of how angular momentum works in extreme gravity. Its existence suggests that supermassive black holes at galactic centers might also reach these near maximum spins, powering some of the brightest quasars in the universe. And if we ever crack the secrets of harnessing this spin energy, well, that's the stuff of interstellar civilizations. Yet for all its ferocity, this black hole is also a reminder of cosmic balance. Its spin can't exceed the theoretical limit without tearing spacetime apart, a built-in speed governor for the universe's most destructive objects. Every rotation is a dance on the edge of possibility, a reminder that even in the darkest corners of space, the laws of physics still call the shots. The universe doesn't just move fast, it delivers. Hurtling toward the Milky Way at 700,000 miles per hour, the Smith Cloud is a monstrous intergalactic delivery truck packed with enough star fuel to birth 2 million suns. This colossal river of hydrogen gas stretches 11,000 light-years long and 2,500 light-years wide, a ghostly ribbon of raw material racing toward our galaxy like a cosmic bullet with a built-in expiration date. What makes this high-speed cloud extraordinary isn't just its velocity, but its inevitable destiny. In roughly 30 million years, it's going to slam into the Milky Way's outer disk and ignite a fireworks show of star formation unlike anything our galaxy has seen in billions of years. Discovered in 1963 by Dutch astronomy student Gail Smith, this gaseous behemoth spent decades puzzling scientists. Early observations showed it had the mass of a small galaxy, yet no stars, just pristine hydrogen chilled to near absolute zero. But the real shock came when Hubble Space Telescope data revealed its composition. The Smith Cloud is packed with sulfur, oxygen, and other heavy elements typically forged inside stars. That means this isn't some primordial relic from the cosmic dawn, it's a recycled marvel, likely ejected from the Milky Way itself in a violent eruption 8 billion years ago. Imagine a galaxy coughing up a lung, only to catch the same lung hurtling back centuries later. The cloud's trajectory reads like celestial poetry. After its ancient expulsion, it spent eons drifting through intergalactic space before gravity finally reeled it back in. Now it's punching through the Milky Way's halo at a 45-degree angle, its leading edge already glowing from collisions with the galaxy's sparse outer gas. Radio telescopes have mapped its elongated tail, twisted like a comet's by the galaxy's magnetic fields, a smoking gun showing the first whispers of collision have already begun. When the main body strikes, simulations predict it'll plow into our galaxy's star-forming regions like a meteor hitting powder kegs, compressing interstellar gas until it collapses into stellar nurseries. But here's the twist, the Smith Cloud isn't alone. Astronomers have identified dozens of similar high-velocity clouds circling the Milky Way, leftovers from an era when galaxies constantly cannibalized their surroundings. Some, like the Magellanic Stream, trail behind dwarf galaxies being devoured by our own. Others might be intergalactic hitchhikers captured from the void between galaxies. Together, they form a hidden conveyor belt of star-making material, a testament to how galaxies grow not just from within, but by snatching riches from the cosmic wilderness. What awaits this interstellar immigrant as it crashes into the Milky Way's disk? Shockwaves will ripple through the gas, triggering chain reactions of star birth. The heaviest elements in the cloud, those same sulfur and oxygen traces, will become the building blocks of rocky planets. Future civilizations might one day gaze at stars born from this collision, never knowing their worlds owe existence to a hypervelocity cloud that crossed the dark for billions of years just to reach them. The Smith Cloud is more than a speed record. It's a reminder that even the emptiest corners of space are alive with motion, and that every galaxy is a work in progress, constantly remaking itself with raw materials flung across the void. When a star explodes, the light from its death throes doesn't just vanish into the void it bounces. Light echoes are one of the universe's most surreal phenomena, where supernova flashes ricochet off interstellar dust clouds, creating ghostly afterimages that replay the explosion in slow motion across centuries. Imagine shouting into a canyon and hearing your voice return seconds later, except here, the canyon is light years wide, and the echo travels at light speed, painting the same cataclysm across the cosmos multiple times from different angles. Take the case of supernova 2006 GY, which erupted in the Large Magellanic Cloud in 1987. The initial flash, brighter than 1 billion suns, was visible to the naked eye, but the real show began decades later. As the light raced outward, it struck dust filaments hundreds of light years away, illuminating them like a flashlight beam revealing cobwebs in a dark room. Each illuminated dust layer became a delayed mirror, reflecting the explosion back to Earth years after the original event. Hubble Space Telescope images captured these echoes as expanding rings of light, each one a replay of the supernova's shockwave from a different cosmic vantage point. The physics behind this illusion is both simple and mind-bending. Light travels at a fixed speed, so when it takes a detour by bouncing off dust, it arrives later than light that came straight to Earth. The farther the dust lies from the supernova, the longer the delay. Some echoes even reveal details the original blast obscured, like catching a glimpse of a fireworks display from behind by watching its reflection in a distant building. But here's what makes light echoes more than just cosmic curiosities. They're time machines. By analyzing the spectrum of reflected light, astronomers can study the composition of ancient supernova long after they fade. In 2022, researchers used echoes from a 17th century supernova to confirm it was a Type Ia explosion, the same kind used to measure cosmic distances. These flickering afterimages also map the Milky Way's hidden dust structures, tracing filaments too faint to see otherwise. Perhaps the most haunting example lies in the Red Square Nebula, where multiple echoes from a 600-year-old supernova cascade through space like ripples in a pond. Each ring freezes the explosion at a different moment, allowing scientists to reconstruct its entire life cycle, something impossible with a single observation. Light echoes blur the line between past and present. Every new reflection is a message from a star already gone, a reminder that in the cosmos, even death doesn't happen just once. When Oumuamua streaked through our solar system in 2017, it wasn't just another space rock. It was an interstellar speed demon blazing through at 196,000 miles per hour, fast enough to outrun the sun's gravity like it was standing still. This cosmic bullet didn't just break speed records, it shattered assumptions, leaving astronomers scrambling to explain its bizarre trajectory and even stranger properties. Unlike any asteroid we'd seen before, this interstellar visitor accelerated as it departed, as if some unseen force were pushing it forward into the void. The numbers alone are staggering. At peak velocity, Oumuamua could have traveled from Earth to the Moon in just 11 hours, a journey that takes our fastest spacecraft days. But what really set scientists' alarms ringing was its path. Most objects slingshotting around the Sun follow predictable curves dictated by gravity. Oumuamua didn't. After whipping past our star at a blistering 196,000 miles per hour, it unexpectedly sped up as though equipped with invisible engines. This wasn't just odd, it was unprecedented. Theories erupted like supernova. Some suggested Oumuamua was a hydrogen iceberg, its surface vaporizing in sunlight like dry ice, creating a natural thruster. Others proposed it might be an ultra-thin shard of nitrogen ice sheared off a Pluto-like exoplanet. Then there was the more speculative but tantalizing idea: could it be artificial? The object's unusual shape, potentially 10 times longer than it was wide, sparked comparisons to science fiction's vision of interstellar probes. While most astronomers dismissed the extraterrestrial hypothesis, the very fact it entered mainstream discussion speaks volumes about how thoroughly Oumuamua defied expectations. What's wild is how little time we had to study it. discovered as it was already leaving the inner solar system, telescopes caught only fleeting glimpses before it vanished into interstellar darkness. Those hurried observations revealed more puzzles. Oumuamua lacked the comet-like tail of gas and dust typical of icy bodies, yet its acceleration suggested outgassing was occurring. This paradox led to radical rethinking of how small celestial objects behave when heated by alien suns. The real treasure lies in what Oumuamua implies about our galaxy. Its speed and trajectory suggest it's been wandering between stars for millions, possibly billions of years, untouched by any solar system until ours. Statistically, for one such object to pass through our neighborhood means space must be teeming with them. Follow-up calculations estimate the Milky Way could contain quadrillions of similar interstellar nomads, outnumbering stars by 1,000 to 1. Each one is a fossil from some distant star system, carrying chemical clues about how planets form in environments utterly unlike our own. Future telescopes like the Vera Rubin Observatory stand ready to catch the next Oumuamua earlier, giving us precious months instead of weeks to unravel its secrets. Until then, this enigmatic visitor remains a cosmic postcard, one with half the writing faded, hinting at stories we're only beginning to decipher. Its record-breaking eggs, it wasn't just a display of speed, it was a challenge flung at our understanding of the universe, daring us to think bigger about what might be sailing through the dark. The Sun's corona has always been a cosmic paradox, a blazing halo of plasma, mysteriously hotter than the star's surface beneath it. For decades, scientists scratched their heads over how this outer atmosphere could reach millions of degrees while the Sun's visible surface simmers at a mere 10,000. The answer, a hidden symphony of magnetic waves crackling through the corona like an invisible orchestra, accelerating the solar wind to 145,000 miles per hour. These aren't ordinary ripples, they're Alfvén waves, named after Nobel laureate Hans Alfvén, who first theorized their existence in 1942. Picture a guitar string stretched across the solar system, vibrating with enough energy to launch charged particles fast enough to escape the Sun's gravity entirely. What makes these waves extraordinary is how they transfer energy. Unlike sound or ocean waves, Alfvén waves ride on magnetic field lines, twisting and snapping like whips through the corona's ionized gas. As they travel outward, they push and heat the plasma, much like how shaking a soda bottle builds pressure until it bursts open. NASA's Parker Solar Probe finally caught this process in action during its daring dives near the Sun, detecting surges of plasma perfectly synchronized with the wave's oscillations. The data revealed something startling. These waves don't just gently nudge particles. They can suddenly accelerate them in explosive bursts, like a surfer catching a rogue wave and rocketing forward. The scale of this phenomenon is hard to overstate. A single Alfvén wave can stretch across hundreds of thousands of miles, channeling energy from the Sun's churning interior into its atmosphere. Some theories suggest these waves might even explain the solar wind's erratic speed variations, which range from a slow 700,000 miles per hour to a blistering 1.8 million. When multiple waves collide, they create turbulence that heats the plasma further, solving part of the corona's temperature puzzle. It's as if the Sun has an invisible heating system, with magnetic fields acting like underground pipes pumping warmth to its atmosphere. But the real magic happens at the microscopic level. As electrons surf these waves, they gain enough energy to break free from the Sun's grip, becoming the solar wind that eventually bathes our entire solar system. Without this process, Earth would be bombarded by far fewer charged particles, no auroras, but also none of the gentle pressure that helps push back against interstellar radiation. The Parker probe's measurements showed these escaping particles often match the precise frequencies of Alfvén waves, like dancers moving in lockstep with their partners. What's fascinating is how this discovery ties into other cosmic phenomena. Similar waves likely ripple through the accretion disks of black holes and the magnetospheres of distant exoplanets. Some astronomers even speculate that unveil waves could play a role in the mysterious heating of other stars' coronae, suggesting a universal mechanism at work across the galaxy. Every time we crack one of the sun's secrets, we're handed a key to unlocking mysteries light years away. The next time you feel sunlight on your skin, remember, it's not just light making that 93 million-mile journey. Invisible waves of magnetic energy are still pulsing through that light, remnants of the same forces that hurl the solar wind into the void. They're the unseen engines of our star's influence, proof that even in the seemingly placid corona, there's a storm of motion waiting to be decoded. Deep within the Crab Nebula's swirling wreckage lies a powerhouse unlike any other, a pulsar spinning 30 times a second while flinging particles into space at a jaw-dropping 99% the speed of light. This isn't just rapid motion, it's a cosmic demolition derby where matter gets whipped into such a frenzy that the entire nebula glows with the energy of 5,000 suns. The culprit, a neutron star no larger than Manhattan, left behind when its progenitor exploded in a supernova witnessed by Chinese astronomers in the year 1054. Today, its pulsar wind, a hurricane of electrons and positrons, carves through the nebula's debris like a blowtorch through fog, illuminating filaments that stretch light years across space. What makes this system extraordinary isn't just the speed, but the choreography. As the pulsar's magnetic field spins, it acts like a colossal generator, producing voltages so intense they rip particles from the star's surface and accelerate them to near light speeds. These particles then slam into the surrounding nebula, creating shock waves that heat gas to millions of degrees. Hubble's images reveal the aftermath, a labyrinth of glowing tendrils where the pulsar wind collides with slower-moving debris, each filament a cosmic graffiti tag written in high-energy physics. The most violent of these collisions occur at the pulsar's termination shock, a boundary where the wind abruptly slows, transferring enough energy to make the entire nebula shine in X-rays. But the real marvel is how this tiny star influences structures 100 times its size. The Crab's iconic shape, those intricate webs of gas aren't just passive debris, they're dynamic sculptures molded by the pulsar's relentless wind. Radio telescopes have caught this interplay in action, showing how the wind injects energy into specific regions, creating bright knots that fade and reignite like cosmic neon signs. Some filaments even exhibit perfectly synchronized brightness fluctuations, pulsing in time with the neutron star's rotation, as if the entire nebula were breathing to its rhythm. This system isn't just a spectacle, it's a laboratory. By studying how the pulsar wind accelerates particles, scientists gain insights into processes that shape everything from supernova remnants to distant quasars. The Crab's pulsar also serves as a cosmic lighthouse, its beams sweeping past Earth 30 times per second with metronomic precision. In 1968, its discovery provided the first concrete evidence linking pulsars to neutron stars, solving a mystery that had puzzled astronomers since their detection. Perhaps most haunting is the nebula's inevitable fate. The pulsar is slowly bleeding energy, its spin decreasing by microseconds each year as it powers the wind. In a few 100,000 years, a blink in cosmic time, the show will end. The filaments will fade, the glow will dim, and the pulsar will become just another dark cinder drifting through the void. But for now, it stands as a testament to destruction and rebirth, a reminder that even in death, stars can set the cosmos ablaze with motion. 6 million miles per hour, that's the speed at which two galaxies in the Bullet Cluster are tearing through each other, a collision so violent it's warping the very fabric of space-time. But the real shock isn't the visible wreckage of stars and gas, it's the ghostly fingerprint of something far stranger, dark matter, exposed for the first time in this cosmic demolition derby. Picture two tidal waves of stars crashing together, but when the spray settles, the water isn't where you expect. That's the haunting beauty of the Bullet Cluster, a celestial traffic accident where the invisible driver left perfect evidence of its existence. The drama unfolded 150 million light-years away, where two galaxy clusters, each thousands of galaxies strong, slammed into one another like titanic freight trains. The visible stars, separated by vast distances, passed through mostly unscathed, like two crowds of people walking through each other in a stadium, but the hot gas filling the space between those stars. That wasn't so lucky. As the clusters collided, this intergalactic plasma, heated to millions of degrees, piled up in a bow shock wave, glowing bright in X-rays like a cosmic bruise. The shape of that shock gave the system its name, a bullet tearing through space. Here's where physics gets weird. When astronomers mapped the cluster's mass using gravitational lensing, the way its gravity bends light from background galaxies, they found the heaviest parts weren't where the X-ray gas had pooled. Instead, the bulk of the mass, about 85% of it, was floating ahead of the collision, completely divorced from the visible wreckage. It was as if a car crash left the passengers unharmed in their seats while the windshields and doors flew off in different directions. This was smoking gun evidence for dark matter, an invisible substance that interacts with gravity but ignores everything else, including the electromagnetic forces that make gas particles slam together and glow. The implications rewrite cosmology. The bullet cluster proved dark matter isn't just theoretical, it's a physical thing that moves independently of regular matter, like oil separating from water. By tracking how the dark matter components sailed through the collision unimpeded, scientists calculated their speed. Those 6 million miles per hour aren't just galactic highway speeds. They're a benchmark for how quickly entire clusters of dark matter can move when gravity flings them. What's even wilder is the aftermath. The dark matter's trajectory suggests these clusters were falling toward each other at nearly 7 million miles per hour before impact, accelerated by gravity over hundreds of millions of years. Today, the system's a fossil record of that violence, with the gas still slowing down like brake lights in a traffic jam while the dark matter zooms ahead, oblivious. It's a reminder that most of the universe's matter doesn't play by the rules we can see. It's out there, racing through the void, shaping galaxies without leaving a trace. For astronomers, the bullet cluster became a Rosetta Stone. Its X-ray glow and lensing patterns now serve as templates for studying other mergers, helping map dark matter's distribution across the cosmos. Some researchers even use these collisions to test whether dark matter particles might occasionally bump into each other, a faint possibility that could reveal their true nature. Every new cluster smash-up we find adds another piece to the puzzle, showing us a universe where the fastest things aren't always the brightest, and where the real action happens in the shadows. Velocity isn't just another star throwing tantrums, it's a cosmic pressure cooker that unleashed the most violent stellar flare ever recorded, hurling particles into space at 99% the speed of light. Picture the sun's worst solar storm, then multiply its energy by 10,000. And you're still not close to the fury of this red dwarf's outburst. In 2008, satellites caught Velocity's eruption in action, a detonation so powerful it briefly outshone the star itself, pumping out enough X-rays to vaporize any nearby planet's atmosphere in seconds. What makes this flare extraordinary isn't just its raw power, but the physics behind its particle acceleration. Unlike our sun's flares, which typically max out at a few million miles per hour, Velocity's magnetic fields are twisted into knots so extreme they act like cosmic slingshots. The star rotates every 4 days 10 times faster than our sun, winding its magnetic fields tighter and tighter until they snap, recoiling with enough force to launch protons to near light speed. These particles didn't just trickle into space. They were fired like bullets from a railgun, their energy signatures matching what physicists see in man-made particle accelerators, except scaled up to stellar proportions. The aftermath played out like a cosmic detective story. NASA's Swift satellite detected the initial X-ray blast, but it was the follow-up radio observations that revealed the true insanity: synchrotron radiation patterns indicative of electrons spiraling through magnetic fields at relativistic speeds. These radio waves weren't the usual static of a stellar flare. They were the shrieks of matter being tortured by forces we can barely replicate on Earth. Here's the twist: Velocity is tiny. Despite its explosive temper, this star weighs just 1/3 as much as the Sun and glows with a meager 1% of its luminosity. That's what makes its flares so terrifying. They're proof that small stars can harbor disproportionately violent magnetic personalities. Astronomers call these outbursts superflares, and they're rewriting our understanding of stellar activity. If a star like this hosted planets, even those in the so-called habitable zone would be sterilized regularly by these particle bombardments. The implications ripple far beyond one cranky red dwarf. Velocity's flare provides a blueprint for understanding similar eruptions across the galaxy, events that could threaten future interstellar missions or even bathe entire planetary systems in deadly radiation. Some scientists now suspect these ultra-fast particles might contribute to the mysterious cosmic rays that pepper our atmosphere, their origins previously traced only to supernova or black holes. What's haunting is how often this might happen. Velocity is young by stellar standards, a mere 300 million years old, and its rapid spin suggests it's got billions of years of flare-ups ahead. Every eruption is a reminder that the universe doesn't care about size when it comes to unleashing chaos. Sometimes the smallest stars hold the darkest tempers, and their outbursts light up the cosmos with more than just fury. They illuminate the extreme limits of what matter can endure. Black holes aren't just cosmic vacuum cleaners, they're also the universe's most powerful leaf blowers, capable of hurling entire rivers of gas into space at nearly half the speed of light. These aren't gentle breezes, they're relativistic disk winds, hurricanes of superheated plasma erupting from the swirling maelstrom of an accretion disk like a cosmic pressure valve gone haywire. Picture a whirlpool where the water doesn't just spiral down. It explodes upward in a geyser moving at 268 million miles per hour, carrying enough energy to reshape entire galaxies. The secret to these supersonic outflows lies in the extreme physics of an accretion disk's chaos. As matter spirals toward a black hole, friction heats it to millions of degrees, creating a glowing donut of plasma so bright it outshines entire galaxies. But not all that material is doomed to fall in. Some gets caught in the black hole's magnetic field lines, twisted like spaghetti around a fork until the tension becomes unbearable. When these lines snap, they slingshot plasma outward along the disk's poles and edges, creating winds so fast they can escape even a supermassive black hole's gravity. X-ray telescopes like Chandra and XMM Newton have caught these winds red-handed. Their spectra show telltale absorption lines from iron atoms moving at 40% light speed, stretched and blurred by relativistic effects. What's staggering isn't just the velocity, but the sheer scale of these eruptions. In galaxy eras 13234-5119, astronomers measured a disk wind carrying the mass of 3 suns per year, enough gas to build a solar system annually, flung into intergalactic space with the force of 1 million supernovae. These outflows don't just dissipate quietly, they plow through surrounding gas like cosmic bulldozers, creating shock waves that can trigger or suppress star formation across thousands of light years. Yet the most surprising twist is how these winds might solve a cosmic mystery. For decades, astronomers puzzled over why some galaxies stop forming stars long before they run out of gas. The answer might lie in black hole feedback, the process where these relativistic winds dump energy into their host galaxies, overheating or ejecting the cold gas needed to make new stars. In ultra-luminous galaxy Markarian 2319, X-ray data revealed winds so powerful they'd cleared out a cavity 250 light-years wide around the black hole, effectively sterilizing the galactic center. These winds aren't destruction for destruction's sake, they're part of a delicate balancing act. Too little outflow and galaxies would choke on their own gas, forming stars so rapidly they'd burn out in a cosmic flash. Too much and they'd wither into barren husks. The 40% light speed ejections are nature's way of regulating growth, ensuring galaxies evolve at just the right pace. The next time you see an X-ray image of a distant galaxy's core, remember those faint spectral lines aren't just data points. They're the fingerprints of a titanic struggle, where matter on the brink of oblivion fights back with enough force to shape the destiny of everything around it. And somewhere out there, a new wind is probably forming, a gale of particles born in darkness, destined to race across the cosmos at speeds we can barely comprehend. NGC 1277 isn't just another galaxy drifting through space. It's a cosmic bullet tearing through the universe at 2,000 kilometers per second, fast enough to cross the entire continental United States in under 2 seconds. What could possibly accelerate something 200,000 light-years wide to such mind-bending speeds? The answer lies in the hidden highways of the cosmos, the vast intergalactic filaments of dark matter that weave the universe into a giant, three-dimensional spiderweb of gravity. These cosmic filaments, strands of invisible matter stretching hundreds of millions of light-years, act like celestial rubber bands. When galaxies fall into them, they can get catapulted to velocities that defy common sense. Here's how it works. As NGC 1277 plunged into one of these filaments, likely drawn in by the collective gravity of a nearby galaxy cluster, it didn't just slow down and settle. Instead, the combined gravitational pull from the filament's dense dark matter and neighboring galaxies slingshotted it forward like a stone from a trebuchet. The result, a spiral galaxy now zooming fast enough to escape the gravitational grasp of its local supercluster entirely, destined to wander the cosmic voids alone. What makes this galaxy's speed even more astonishing is its sheer size. Most hypervelocity objects we've discovered, like rogue stars or small galaxies, are relatively lightweight, making their acceleration easier to explain. But NGC 1277 is a monster, packing nearly twice the mass of the Milky Way. To fling something this enormous requires forces so extreme they'd make supernova explosions look like firecrackers. Astronomers suspect it got an extra boost from a rare cosmic alignment, multiple filaments converging at just the right angle to multiply the slingshot effect. The evidence lies in the galaxy's pristine condition. Unlike galaxies that get torn apart by cluster collisions, NGC 1277's spiral arms remain intact, its stars undisturbed. This suggests it didn't earn its speed through a violent crash, but through a smoother, more precise gravitational assist, like a surfer catching the perfect wave. X-ray observations reveal another clue: the absence of hot gas trailing behind it, confirming it's moving too fast for interstellar material to keep up. But NGC 1277 isn't alone in this hypervelocity club. Surveys have identified dozens of similar runaway galaxies, each with its own unique trajectory. Some, like the elliptical galaxy 3C318, were likely ejected after close encounters with supermassive black holes. Others might be fleeing the gravitational tug of war between merging galaxy clusters. Together, they're rewriting our understanding of how large-scale structures shape galactic motion. The real revelation here is what these speed demons teach us about dark matter's role in cosmic evolution. By tracking their paths backward, astronomers can map the otherwise invisible filaments that make up the universe's backbone. Each hyperfast galaxy is like a tracer die flushed through hidden plumbing, revealing the architecture of the cosmic web. Future telescopes like the Roman Space Telescope aim to find thousands more of these intergalactic sprinters, using them to chart the gravitational highways that have guided the universe's growth since the dawn of time. Imagine being on board a planet in NGC 1277 looking up. You'd see neighboring galaxies redshifted into oblivion as your home tears through the cosmos, leaving familiar constellations behind at incomprehensible speed. Yet even at this pace, the galaxy's journey would seem frozen on human timescales, a reminder that the universe's fastest phenomena unfold across epochs, not years. These runaway galaxies are more than curiosities. They're proof that the cosmos is constantly in motion, propelled by forces we're only beginning to measure. SN 1006 wasn't just a bright light in the night sky when it exploded in the year 1006. It became a cosmic particle accelerator so powerful it's still hurling matter at near light speeds a millennium later. The remnant of that ancient supernova, located 7,000 light-years away, boasts the fastest shockwaves ever detected, racing outward at 9 million miles per hour. That's fast enough to cross the entire United States in less than 2 seconds, leaving behind a turbulent wake where atomic particles get whipped to energies beyond anything humanity's most powerful colliders can produce. What makes these shockwaves special isn't just their speed, it's how they turn destruction into creation. As the explosion's debris plows into interstellar gas at 20 times the speed of sound, it doesn't just push material aside. It superheats and ionizes everything in its path, transforming a gentle cosmic breeze into a searing plasma storm. Electrons caught in this chaos get catapulted to 99.99% light speed, spiraling along magnetic field lines until they emit eerie blue X-rays, a phenomenon called synchrotron radiation. The result, a 200 light-year-wide bubble glowing with the energy of 100 suns, its edges shimmering like a cosmic neon sign. But here's where it gets truly bizarre. Particles accelerated by these shocks don't just zoom off into space, they ricochet back and forth across the shock front like ping-pong balls trapped between two paddles. Each collision boosts their energy further in a process called Fermi acceleration, named after physicist Enrico Fermi, who first theorized this cosmic pinball machine. Some protons here reach energies so extreme they become Ni particles, named for the sharp bend they create in cosmic ray energy graphs, carrying 1,000,000 times more oomph than anything the Large Hadron Collider can muster. The real magic lies in the shockwave structure. Unlike the smooth wavefronts we see in water, supernova shocks are riddled with cosmic potholes, turbulent knots where magnetic fields twist into pretzel shapes, creating perfect traps for high-energy particles. Chandra X-ray observatory images reveal these wrinkles in stunning detail, showing filaments where electrons are being accelerated so violently they blur the line between matter and energy. Some regions glow brighter than others, marking cosmic speed traps where particles get an extra kick from rippling shock surfaces. This isn't just a spectacle, it's a clue to one of astronomy's biggest mysteries. Many astrophysicists believe these supernova shockwaves are the primary factories for galactic cosmic rays, those high-energy particles that constantly pepper Earth's atmosphere. SN 1006's shock proves the process in action, showing how stellar death throes can forge the atomic bullets that shape everything from cloud formation to potential mutations in DNA. Every raindrop that falls on Earth carries traces of heavy elements forged in similar explosions, while the air we breathe is constantly ionized by their distant shockwaves' offspring. Perhaps most haunting is the time scale. While the original explosion faded from view centuries ago, the shock front keeps expanding, its energy slowly dissipating into the interstellar medium. In another few millennia, it'll vanish entirely, but not before seeding the galaxy with particles that might one day trigger star formation in distant gas clouds. The universe has a way of recycling its violence, turning cataclysm into creation at speeds that defy imagination. So the next time you look up at the night sky, remember, somewhere out there, shockwaves from long-dead stars are still racing through the dark, carrying echoes of detonations our ancestors once marveled at as temporary stars. We're just beginning to understand how that violence sculpts the cosmos we call home. Imagine a star's final moments not fading quietly into darkness, but being ripped into a blazing spiral of doom, stretched so thin that it becomes a stream of superheated plasma circling a black hole at nearly the speed of light. This is a tidal disruption event, one of the universe's most violent spectacles, where gravity doesn't just kill, it unravels. When a star drifts too close to a supermassive black hole, the difference in gravitational pull between its near and far sides becomes so extreme that the star isn't just torn apart, it's spaghettified, stretched into a filament of glowing debris spiraling toward oblivion at relativistic speeds. The physics behind this cosmic shredding is both elegant and terrifying. As the star crosses the black hole's Roche limit, the point where gravity overwhelms the star's self-binding energy, its outer layers balloon outward while its core compresses like taffy being pulled apart. What happens next depends on the black hole's size. For smaller black holes, the star gets completely disrupted before reaching the event horizon, creating a luminous accretion disk of stellar debris. But with supermassive black holes, the process is even more gruesome. The star may orbit several times, enduring multiple rounds of stretching and compression before finally succumbing. The aftermath is where the real fireworks begin. As the stellar debris spirals inward, friction heats it to millions of degrees, emitting a flare of X-rays and ultraviolet light so bright it can outshine an entire galaxy for months. In 2019, astronomers witnessed one of these events dubbed at 2019 KISS, where nearly half the star's mass was flung into orbit at 30% light speed, while the rest vanished beyond the event horizon. The data revealed something astonishing. The debris didn't just form a neat disk. Instead, it clumped into turbulent streams, some ricocheting back outward in colossal loops powered by magnetic fields and shock waves. What makes tidal disruptions so scientifically precious isn't just their violence, it's their rarity. Most galaxies experience only one every 10,000 to 100,000 years, making each detection a golden opportunity. By studying the light curves of these flares, astronomers can measure the black hole's spin, probe the star's composition, and even test general relativity in extreme gravity. Some disruptions, like Assassin 14 Li, even produce relativistic jets, beams of particles shot outward at near light speed, hinting that black holes don't just consume matter but sometimes spit it back out with unimaginable force. Perhaps the most haunting detail is the star's legacy. The elements forged in its core, carbon, oxygen, iron, are now scattered across the accretion disk, some eventually escaping into space to seed future generations of stars and planets. In death, the star becomes part of the black hole's growth, its energy fueling the very monster that destroyed it. It's a reminder that even in destruction, the universe finds a way to recycle, rebuild, and rewrite the rules of existence. Tidal disruptions are more than cosmic demolition derbies. They're windows into the most extreme gravity wells in existence. Every flare, every jet, every twisted stream of debris carries clues about how black holes shape their surroundings, how matter behaves under unbearable strain, and how the universe balances creation and annihilation on scales we're only beginning to fathom. Here's a paradox that bends the rules of reality itself: galaxies so distant they're fleeing from us faster than light can travel. Not because they're breaking cosmic speed limits, but because the fabric of space between us is stretching like an infinite rubber band, carrying them away in a current no object could ever hope to outrun. This isn't science fiction, it's the unsettling reality of our expanding universe, where Einstein's rules hold firm locally, but the grand cosmic stage itself is growing at scales that defy everyday intuition. Picture space as a rising loaf of raisin bread, where each raisin represents a galaxy. As the dough expands, nearby raisins drift apart slowly, while those farther away separate more rapidly, not because they're moving through the dough, but because more dough stretches between them. Now imagine two raisins so far apart that the dough between them expands faster than any single raisin could theoretically move. That's precisely what's happening across cosmic distances. Galaxies beyond our Hubble volume, a bubble of space about 14 billion light-years wide, are disappearing from view forever, their light stretched into irrelevance by the relentless expansion of spacetime itself. The engine behind this acceleration, dark energy, a mysterious force making up 68% of the cosmos, acting like anti-gravity on galactic scales. While gravity pulls matter together, dark energy pushes space apart, and its influence grows as the universe expands. Telescopes have captured the evidence. Supernova in distant galaxies appear dimmer than expected, proving the expansion wasn't slowing down as once assumed, but speeding up. The most distant galaxy ever measured, HD1, is racing away at what would be 5 times light speed if it were moving through space, but here's the catch: it's not moving at all in the traditional sense. Space itself is swelling beneath it, carrying it along like a surfer on an endless wave. This phenomenon shatters a common misconception, the idea that nothing can exceed light speed. Einstein's limit applies only to motion through space, not to the expansion of space. It's the difference between a fish swimming in a river never surpassing water's wave speed, and the river itself lengthening as new water appears between its banks. For galaxies beyond the cosmic horizon, their light will never reach us, not because they're too far away now, but because the space yet to be crossed is growing faster than light can hope to bridge it. What's truly humbling is the fate this implies. In 1 trillion years, any civilizations arising in our local galaxy group will see only blackness beyond Andromeda. The rest of the universe will have vanished from their sky, its light stretched beyond detection. All evidence of the Big Bang, dark energy, or an expanding cosmos will be erased, leaving future astronomers with no clues that galaxies ever existed beyond their tiny island of stars. Yet this expansion isn't empty destruction, it's the universe's creative engine. The same stretching that pulls galaxies apart also cools the cosmic background radiation, allows gravitational structures to form, and even makes life possible by giving atoms room to exist. Without this acceleration, stars might never have ignited, and planets might never have formed. The very force that isolates us in the distant future also set the stage for our existence now. So when you look up at the night sky, remember those distant pinpricks of light are on a one-way trip into darkness, not by their own motion, but by the silent, unstoppable stretching of the stage beneath them. And somewhere beyond what we can see, the universe is growing faster than light can hope to chase, carrying mysteries we'll never witness into the eternal dark. From hypervelocity stars ejected at 1 million miles per hour to black holes spinning spacetime into a frenzy with over 1,000 rotations every second, we've raced through 30 of the universe's most mind-blowing speed demons. Think about pulsars whipping around faster than a kitchen blender, or gamma-ray bursts launching matter at 99.99% light speed, forging gold in their wake. Picture rogue black holes flung from galaxies at 4 million miles per hour, or entire galaxy clusters colliding so violently they separate dark matter from visible gas. These aren't just record breakers, they're cosmic laboratories, rewriting the rules of physics under conditions we can't replicate on Earth. Consider the sheer diversity of these speedsters: neutron stars with surfaces moving at 1/4 light speed, or the Smith cloud, a hydrogen bullet 6 times faster than a supernova's shockwave barreling toward the Milky Way to spark future stars. Dark matter rivers flow unseen at millions of miles per hour, while quasars blast winds so powerful they sculpt galaxies. And let's not forget Oumuamua, the interstellar visitor that defied gravity itself as it zoomed past the sun. Even time and space aren't safe, with distant galaxies vanishing faster than light can chase them, thanks to the universe's relentless expansion. Every one of these phenomena forces us to rethink what's possible. Einstein's theories bend but don't break under these extremes, revealing black holes that stretch stars into spaghetti, or particles like the, oh my god, proton hitting energies beyond anything our colliders can match. Yet for all we've discovered, each answer births new questions. How do pulsars spin so fast without flying apart? What cosmic slingshot launched NGC 1277 across the void? And just how much faster can the universe push matter before physics as we know it unravels? Now it's your turn. Which of these cosmic speedsters left you stunned? Was it the star orbiting a black hole every 7.6 years, or the gamma-ray burst that outshone the entire universe for a few seconds? Drop your pick in the comments and let's geek out over the universe's need for speed together. And if you're hungry for more mind-bending cosmic wonders, hit that subscribe button. We've got a universe of mysteries left to explore. Until next time, keep looking up, because out there, the cosmos is always breaking its own record.